It starts all the way back at the beginning of the universe, 14 billion years ago, with the Big Bang and formation of everything, when back then everything was just hydrogen and helium and a little bit of some other stuff. But stars and galaxies began to form, and they were like factories for creating new elements. Really big stars formed, and they exploded as supernova. And this seeded the universe with everything heavier than iron, was born in these final moments of a supernova explosion. Now, two of the things that were created in the supernova are what I want to talk about today, thorium and uranium. These were different because they were radioactive, and they kept some of that energy from the supernova explosion stored in their very nuclear structure. And these materials, along with all the others, came together to form our solar system and our planet billions of years ago. And some of this thorium and uranium then was incorporated into our planet, sinking to the center of the world and heating our planet, generating this energy that generates the Earth's magnetic field, and it drives plate tectonics, and it has spread apart oceans and pushed up mountains. And these materials, thorium and uranium, are now incorporated into minerals all over the world. But because thorium has a longer half-life, it's about 3 times more common than uranium. This is the most rich deposit of thorium in North America. It's found in Idaho. Now, as life filled the world, protected by the magnetic field, it didn't know anymore about the importance of these minerals, and certainly we didn't as we entered the scene. We made our future out of stones and simple tools because they were resistant to fire and they were rugged. When we were able to find metals like gold, we practically worshiped them because they were so marvelous and shiny. But gold was far too rare to build an industrial civilization around. We couldn't build a plow out of gold or armor or spears. Bronze was the material we wanted to use because it was much more common. And the technologies that allowed us to first smelt iron were really what led to many modern innovations we have today. Iron is still the most commonly used of all the metals. And thousands of years of human history, only 7 metals were known. Chemistry and technology really began in the 1700s, and it was centered in this place, the Royal Institution in London. This was a golden age of science. In the basement of the Royal Institution, 10 elements were discovered. For instance, common table salt is composed of sodium metal and chlorine gas. In 1829, a Swedish scientist named Jan Jacob Berzelius isolated thorium, and he gave it this awesome name, named after the Norse god of thunder. He had absolutely no idea how well he had named this element. In fact, it's probably the best named element in the history of all elements. He didn't understand any of that, though. In 1841, uranium was also discovered using the same potassium that had been discovered in the basement of the Royal Institution. Now, this fellow also deserves special mention. His name is Henri Moissan, and he was the French scientist who first synthesized fluorine. Well, what's special about fluorine? Well, it's the most reactive of all the elements that we know of. It's so reactive, in fact, we never find it in nature by itself. We always find it combined with other things like calcium or sodium or so forth. But the important thing to understand about fluorine is when it combines with a metal, it forms very, very, very stable compounds. This example is lithium fluoride. That may sound strange, but I'll bet a number of you brushed your teeth this morning with a fluoride salt called sodium fluoride. So if this looks familiar to you, you're already well acquainted with this technology. But one of the most important things that happened with fluorine was this gave us the ability, finally, to synthesize aluminum. And aluminum became an incredibly important metal to our modern world. We would not have airplanes, and we would not have rockets if we had not been able to develop aluminum. And fluorine was actually the key to the development of aluminum. Now, in the late 1800s, this lady, Marie Curie, was trying to understand what made thorium and uranium different than the other elements. Why were they radioactive? And she devoted her life to trying to understand this mystery. Thanks to her work and others, an understanding of the atom developed. And it was found to be kind of like a little solar system. Now, physicists might cringe as I say this because it's not exactly right, but it's mostly right. There's a proton and there's a neutron and these particles at the nucleus, and then there's these little tiny electrons spinning around this. And this was very important because this finally helped them crack the mystery of what the heck was radioactivity. Radioactivity was a war going on inside the atom between the positively charged protons that were trying to pull away from one another and the neutrons and the protons, which both exerted a force called the nuclear force that helped glue them together. Radioactivity happened when there were too many or too few neutrons for however many protons you had. And also it explained why certain elements, when they got too heavy, were always radioactive. This explained thorium and uranium, and indirectly why we have energy from inside the Earth, geothermal energy, all of these things. It explained why we have the forms of uranium and thorium we have today. There's only 3 natural forms of radioactive material. One of them is found in thorium. It's 14 billion years old, and then 2 more are found in uranium. Now, the part of uranium that we use for nuclear energy now is just a tiny, tiny, tiny amount. It's only 7 parts in 1,000 of the natural uranium is used for energy. And in 1938, 2 scientists, Otto Hahn and Lise Meitner in Germany, discovered that small amount of uranium could be fissioned. It could be split apart, and that released neutrons and much, much, much more energy. And this was a great discovery that thrilled scientists around the world. But the leadership in Germany kind of looked at the whole thing askance because Meitner was Jewish, and she had fled Germany to Sweden to escape the Nazis. But scientists in the United States, particularly Jewish scientists that had fled Europe, were paying very, very close attention to this work, and they were trying to alert the government that research was probably going to be going on in using uranium as an explosive. So they knew that they would need to go and change the amount of uranium that was this very rare stuff. And this is where fluorine came to the rescue again. By combining fluorine with uranium, 6 fluorine atoms for each uranium atom, they were able to make uranium into a gas that was suitable for increasing or enriching the concentration of uranium-235. Now, this whole technology would not have worked if fluorine had different properties, but fortunately, fluorine only has one kind of structure. 9 protons, 10 neutrons, no other kind. And that's what allows it, in this form, to preserve that very, very delicate balance between the heavier form of uranium and the lighter form of uranium. The story for thorium, ironically, though, begins with this fellow. His name was Glenn Seaborg, and he was a chemist at the University of California in Berkeley. In 1939, he was following the work in Germany very, very closely. And he wanted to know if other elements could be used for nuclear energy. He had access to the most powerful nuclear physics machine in the world. It was called the cyclotron. And with this machine, he was able to bombard uranium and thorium with neutrons, and he discovered new elements, neptunium and plutonium, and he also discovered a new form of uranium called uranium-233. With more work on the cyclotron, he discovered that both plutonium and uranium-233 could also be turned into nuclear fuels. And so in a very short period of time, Seaborg had discovered a way to turn all of these nuclear fuels into potential energy sources. And this was a discovery that had profound implications for the world. Unfortunately, it was discovered at exactly the wrong time because this was the middle of World War II and everything was being devoted into a wartime effort. Before long, Seaborg was read into a secret program called the Manhattan Project, and he was instructed to go and use his discovery of plutonium to prepare materials for a nuclear weapon. Not long thereafter, the Japanese attacked Pearl Harbor and the United States was launched into World War II. Seaborg was also still very curious about thorium, so he made sure that one of the first reactors that was built was loaded with some thorium so that he could learn more about its properties. Unfortunately, he wanted to find out if he could use thorium as a nuclear weapon because it was during wartime. When the results came back, he was very surprised. He found out that thorium was really going to be totally lousy for a nuclear weapon because the uranium-233 that would be formed was always going to be contaminated with other things that were going to emit large amounts of radiation. But he discovered something that I think is still very important for us to know about today, which is that uranium-233 had a property where it could continue to make enough neutrons in its fission to create new uranium-233 at an equal or greater rate than it was consumed. And this meant that thorium could be used as a nuclear fuel that would last essentially as long as the thorium lasted. And because thorium was so common, this meant that we would have an energy source that would essentially never run out. But again, all of these realizations were swept away by the wartime need for a nuclear explosion. And the United States was the only country that had the technology for nuclear explosions. And they had a big secret, which was that they were out of bombs after World War II. And so all of their effort went into making more nuclear weapons. They did not put effort into how can we go and make nuclear energy. There was great controversy over who should be in charge. Ultimately, they decided they were going to create a civilian agency, but they gave it a military mission. I say all these things with great regret because I'm convinced that had nuclear fission been discovered at some other time in human history, we would have had a very, very different story. If your first introduction to something is very negative, you tend to think about it negatively from then on. People were not thinking about how to use nuclear energy for positive purposes because of the wartime effort. And so it's one of these great tragedies of how our history evolved that nuclear attained such a negative impression in people's minds from the outset. After the war, there was a tiny focus on making some nuclear energy using a sodium reactor, and this was because it had the ability to make more plutonium and better plutonium than it consumed. But this fellow, Alvin Weinberg, he also was somebody who chose to start. He chose to start looking at thorium at the Oak Ridge National Labs after the war, and his efforts in thorium were spurred because he had gotten a contract from the Air Force to look at a power source for a bomber. He wasn't particularly interested in nuclear bombers, but he knew it was going to be a way to develop a new and advanced reactor. And this was the reactor they came up with. It was called the aircraft reactor experiment, and it was the first reactor to use these fluoride salts successfully. The reactor program was canceled, but at the same time, another group of industrialists was looking at using the sodium reactor and advancing that technology. They wanted to build a sodium reactor that would make lots of plutonium, and they put a lot of money and effort into building this consortium of utilities and began building this reactor. It was completed in 1963, and not long thereafter, unfortunately suffered a meltdown and was very concerning to a lot of people who were living in Michigan at the time. At the same time, Weinberg was designing a reactor that was completely immune to the idea of nuclear meltdowns or nuclear accidents. By using this fluoride salt and its stability that it had because of its chemical properties, they were able to design a reactor that wouldn't melt down. It wouldn't have any of these problems. It would operate at low pressures, but yet at high temperatures. And it would have safety features that were really far in advance, even of anything we have today. They successfully built and operated this reactor. In fact, Glenn Seaborg here was at the controls of the reactor when it used uranium-233 as its first fuel load. They were very pleased with the success of this reactor in 1969, but unfortunately, budget cuts, which had been instituted by Richard Nixon, meant that the Atomic Energy Commission could only go forward with one kind of reactor, and they didn't choose the thorium reactor. They chose the plutonium fast breeder reactor. They wanted to build another one in the 1970s, and this program ultimately went on to be canceled. But even after it was canceled, they didn't go back and say, well, what about thorium? Was that a good idea? Was that perhaps a better choice that we should have taken? To me, this is one of the great regrets, again, that this technology path was not chosen. The United States went on to complete almost 100 nuclear reactors in the 1980s and the 1990s, but really things started to bottom out in the 90s in the nuclear field. There weren't new reactors being built. There wasn't new technology being developed. Now we do have 2 new nuclear reactors under construction in Georgia, but we're closing down nuclear reactors faster than we're opening them. And we still have an issue with nuclear waste. What are we going to do about long-term nuclear waste? It's an unsolved issue, and it concerns a lot of people. One of the great advantages of the thorium approach is that thorium does not produce the long-lived nuclear waste that the uranium fuel cycle does. And this is because it starts from a different position on the periodic table and is able to have more opportunities to consume all of its nuclear fuel rather than to produce long-lived nuclear waste. These fluoride salts that I've mentioned are really an ideal fuel for creating safe, easily operable reactors that can use thorium efficiently, and they can also burn up the kinds of nuclear waste we've already produced. They would be very, very good at this task. Because they operate at low pressures, they don't need big containment structures like existing reactors do, and this allows them to be built in factories for a lot less money. Because we know that we're going to need to go forward with producing more energy at lower cost and creating less pollution and less challenge to our environment. So I have been working on a design for a modular nuclear reactor based on thorium and these fluoride salts that has got me very excited because not only will it produce electricity, but it will also produce desalinated water, and it will also produce particular nuclear medicines that are in great demand. Things like this aren't helpful because I really think this is totally wrong. I don't think nuclear is the dream that failed. I think what happened was the way we went in nuclear was shaped by the wrong influences. We were shaped by a desire for things related to war rather than things related to energy and electricity and things that help people. So several years ago, as I was pondering whether or not I should make this leap into starting a new company, I had to really think hard because I was in a great job. I loved it. I had a new baby. It just really didn't seem like the right time. But I found out that other countries were going forward with new nuclear reactor technology using thorium and fluoride salts. And I really felt like unless I made the decision to start working on this, it wasn't going to happen. I've been doing technology development long enough to know these things don't happen on their own. They happen because somebody decides to do them. And so just a few months before I got started, the Fukushima accident happened in Japan, and I really, again, had to wonder, is this the right move to make? But then when I considered the fundamentals, that people were not going to stop wanting energy, they were not going to stop wanting reliability, and they were definitely going to keep wanting to have as clean energy as was possible, I knew really there was no other choice. I had to go forward. And it's been tough. I've learned a lot of things since then. I've learned that when you're 36 years old and you got a wife and kids, you're not exactly the kind of investment your typical venture capitalist is looking for. I might have done better if I wore a hoodie and ate some more pizza. I also realized that nuclear reactors are not iPhone apps or anything like that. This isn't the kind of in-and-out type investment that most investors are looking for. So it's been an eye-opening experience, but I've met some really great people, and I've been really grateful for letters of support that I've gotten from all over the world. People who say, keep at it, keep up the good work. I know this is going to make a difference in our future, and we're going to turn out better for it. And really, if I could just leave you with my belief that each of us has to make a choice of what can we do to make the world the best place. I think the best thing I can do for the world is to be a great dad for my family, and the next best thing I can do is to try to use my talents to bring about an energy source that can benefit all of us. And I just want to leave you with the idea that please, use your talents and your abilities and choose to start to make the best kind of future you can. Thank you very much.